LeetCode question 322 coin change. So you're given an integer array, coins representing coins of different denominations and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. You may assume that you have an infinite number of each kind of coin. So here is an example. We have coins 1, 2, and 5, and the amount that we need to make is 11. The output is 3 coins. 3 coins are needed to make the amount 11. And those coins are 5, 5, and 1. Remember, we can have an infinite amount of any of these coins, so we have chosen 5 twice here, plus 1. Okay, so this is a very tricky question. There are a number of different ways that we can computate this answer. We can use a depth first search, recursive solution, we can use breadth first search, but because this question is asking for the fewest number of coins, so it's asking for an optimal, so anything like the fewest number, the greatest number, the highest amount, the lowest amount, usually is looking for the optimized approach of dynamic programming as the solution. So let's discuss DP. There are 2 possible ways of carrying out DP. There is a top-down, where you start from 11 and branch out and work your way down through possible solutions, or there is bottom-up, and bottom-up is the approach we're going to be taking. So bottom-up requires you to start at the smallest possible amount, so say we chose the amount of 0, and work out the solution of that amount, and then we'll work out the solution of the next value to that, so that will be 1, and then we'll work out the solution to 2, 3, 4, etc. So we're going to create solutions to subproblems, and then we can ultimately use previous subproblems in order to generate the actual solution to 11. So with our DP bottom-up solution, we need a DP array, and our DP array is going to store all the solutions to the values between 0 and 11. So we need our DP array to contain amount plus 1 values. So once we have created this, we need to initialize the DP array with a certain value. Now remember, from the question it asked us to return -1 if we couldn't find a valid solution, so if no coins would add up to the value. So say we had coins and we had an amount of 2. No coins will ever make up 2. So in this case, we need to be able to return -1. So what we need to initialize the DP array with is an invalid value. So if we initialize it with, say, positive infinity, and we initialize each and every value with positive infinity, then if at the end, say in this example, we have infinity at the end, we can say if DP at current amount is greater than the actual amount, then we can return -1. Else, return DP at current amount with positive infinity. So now that that's the DP array sorted, we can start adding values in here. So firstly, with this dynamic programming solution, we can add a base case to this. And the base case in this example is going to be DP at 0. So how many coins does it take to make 0? It's going to take 0 coins to make 0. So now we've updated the infinity with 0, and now we can carry out this process. So how many coins does it take to make 1? Well, we need to loop through the coins, right? So we're going to start off with 1. We're going to check. So the current amount of 1 is within coins array. So we can just say it takes 1 coin from the coin array to make the current amount of 1. Move along. So at 2, we can again loop through the coins array. So we can see that 2 is within the coins array. So we can just update that with 1 coin because 2 is here. That is 1 coin. We'll add it into the DP array. Now moving on to 3, let's check this. So DP at 3, if we start off and we look at 1, so we have taken the coin 1, so that counts as 1 coin. And we are going to add the remainder. So we're going to add the amount, the current amount, minus the coin that we just took. So -1 gives us 2. And the minimum amount of coins it takes to make 2 is 1. So that's 1 plus 1, which is equal to 2. So we can put this in here as a temporary value. Then we need to go across again to the second coin, which is 2. So that counts as 1 coin. And then we need to do the current amount minus 2, which gives us 1. And that is also 1. So that is equal to 2. And lastly, when we get to 5, well, the current amount minus the coin is less than 0. So we can exclude that. We can add that as an if clause. So we can say if current amount, which at this moment in time is 3, minus the coin, 5, is less than 0, then return. So now that we've done that, we can move on to 4. So DP at 4 is equal. If we choose 1, that counts as 1 coin. Then we have to do the current amount minus 1, which is equal to 3. So 1 plus 2 is equal to 3. we can add 3 in there as a temporary value, but we still need to check the other coins for a minimal. So we move over to 2. 2 counts as 1 coin, and then we do current amount minus 2, which is equal to 2. The smallest or the minimum amount of coins needed to make 2 is 1, so we add that on, and that is equal to 2. So that is smaller than 3, so we can update this to 2. Then we move on to 5. Current amount minus 5 is less than 0, so we don't include that. So now we can move along. So as you can see, there's a pattern here, and this is what's called the recurrence relation. So dp at current amount is equal to the minimum between dp at current amount, or 1 plus dp current amount minus coin. So if we look at 5 now, we can see that coins contains 5, so we can just add 1 into there. So if we move on to 6, we start off with 1, so dp at 6 is equal to 1 plus 6 minus 1, so 6, so here we have 1 plus dp current amount minus coin. So current amount is 6 minus coin, so we've got 1. So we work out the dp of that, so that's 1. So that's equal to 2. We can add 2 as a temporary value and check the others to see if there's an even smaller value. So dp at current amount is now 2. So dp down here becomes 2. So then we move on to the next coin. We take 2, so that counts as 1, plus the current amount minus 2, which is 4. So that's plus 2, so that's equal to 3. So 1 plus dp at current amount minus coin is 3. Which one is minimum? 2. So we can keep this as 2. Okay, and then if we moved on to 5, 5 counts as 1 coin. 6 minus 5 is equal to 1. So that counts as 1 again. So 1 plus dp at current amount minus coin is equal to 2. So we can keep 2 there. And then we can carry out this process for the rest of the values. So dp at 7, if we choose 1, we have 1 plus 7 minus 6, which is 1. So that's 1 plus 1, which is equal to 2. We can choose 2 to begin with. We have our current amount at the minute, dp at current amount is equal to 2. If we choose 2, that's going to be equal to 1 plus 7 minus 2, which is 5. So that's going to be 1 again. So that's equal to 2. So that's 2. So the minimum is still 2. If we choose 5 now, that's 1 plus 7 minus 5, which is equal to 2. So that's again 1, which is equal to 2. dp at 8, if we choose 1, it's 1 plus 8 minus 1, which is 7, so that's equal to 2, so that's equal to 3. So current amount, dp is currently 3. So if we move over 2, that's 1 plus 8 minus 2, which is 6, so that's equal to 2, so that's equal to 3 as well. So those are the same. Then we move over to 5, we have, that counts as 1 coin, 8 minus 5, which is equal to 3, that's 2, so that's also equal to 3. So we add 3 in there. dp at 9, we take 1, so that's 1 plus, current amount is infinity. 1 plus 9 minus 1, which is 8, so that's 3, so that's equal to 4. 4 against infinity, which one's smaller? 4, so we can add 4 in there as a temporary value. So 4 becomes dp at current amount. This gets emptied. We move across the coin, so if we take 2, that's going to be 1 coin plus 9 minus 2, which is 7. So 1 plus 2 is equal to 3. 3 is less than 4, so we update here with 3, so that becomes 3. This is emptied. We move across to the next coin. We have 5, so that counts as 1 coin, plus 9 minus 5, which is equal to 4. So that's 2, which is equal to 3. 3 and 3, both the same value, so we can leave that as is. dp at 10, if we take 1, that counts as 1 coin, plus 10 minus 1, which is equal to 9, so that's 3, so that's equal to 4. So infinity against 4, which is smaller, 4 is, so we add 4 in there. So this becomes 4, this is removed. We move it over to the second coin, so that's 1 plus 10 minus 2, which is equal to 8, so that's 3 again, so that's going to equal 4. So 4 stays there. And then lastly, we choose 5, which counts as 1 coin, plus 10 minus 5, which is equal to 1 in the dp array, so that's equal to 2. So 4 against 2, 2 is the minimal. And lastly, for dp at 11, if we choose 1, that counts as 1 coin, plus 11 minus 1, which is 2, so that's equal to 3. So infinity against 3, 3 is the minimum, so 3 can go in there as a temporary value. This goes to 3, this is emptied. We move over to the second coin, so that counts as 1, plus 11 minus 2, which is 9, 3, so that's equal to 4. 4 is not less than 3, so we can forget about that. We move over to 5, that counts as 1 coin, plus 11 minus 5, which is 6, So that's 2, so that's equal to 3. And 3 is the same as 3, so we can keep that in there. Now that this array is full, we can just return dp at amount. And remember, we need to make sure that we have that if conditional logic, just in case this value is still infinity. So in the case of this example up here, if the last value is infinity, we need to return -1. So I'll show you that when we code this out. Firstly, let's discuss time and space complexity. So time complexity is O s times n, where s is the amount and n is the denomination count, and then space is O s, where s is the amount to change. So when writing this out, it doesn't actually take much code. So firstly, if we create the dp array, so we say array amount plus 1, because we want to have 0 up to amount, so we need to add that extra value. And then we need to fill it with an invalid value, so that's going to be infinity. We can set the base case for this dp solution, so dp at 0 is going to be equal to 0 because it takes 0 coins to make the value of 0. So we need to create that for loop. Current amount is equal to 1 because we've already carried out 0 up here. Current amount needs to be less than or equal to amount, and then we can have current amount plus plus. Now we need to loop through the coins. So coin of coins. If current amount minus coin is greater than or equal to 0, then we have a potential value. Because remember, if it's less than 0, then we just forget about it because it's not a valid solution. Then we can say dp at current amount. So now we're going to start filling out that dp array, and that's going to be equal to the recurrence relation we created. So it's going to be equal to math.min dp at current amount for the current value within dp and 1 plus dp at current amount minus coin. So we're going to loop through the coins, we're going to check the coin, minus the coin's value from current amount, and we're going to add a 1 here. And this 1 here resembles the current coin that we have taken. And then to end off, we need to include the if conditional logic, which determines whether the value is equal to -1 or the dp at amount. So we need to return dp at amount. If that is greater than amount, so if it's infinity, we can return -1, else we can actually return dp at amount. Let's just check to see if that's worked. Okay, it's been accepted, let's submit it. And there you have it.